Hello everyone, my name is Sanjit, and today we are going to understand what is the limitation of the conventional materials and why we need new materials like metamaterials. So let's understand this. So first, there is a difference between conventional acoustic materials, which you have seen in the market, and people generally use for noise control, like glass wool, rock wool, foam, perforated panel. These are the conventional material, but these have some limitation. They have some drawback. We will discuss in detail in further slides. And then second category is metamaterials, and you can see the structure of the metamaterial. You can see that these are different from the conventional material, and you can see there is a microstructure inside the material, and this is called the engineering material. And you can see there is a different design. You can see here that's like Helmholtz resonators, that zigzag path. You can uh, see here zigzag path here, and this is the Helmholtz resonator, one neck and the cavity. And you can see here this is the cavity of different uh, resonance or local resonance, you can say. So the question is that why do we need new materials or acoustic materials? Let's figure it out. So first we are going to understand this simple wall. Sometimes we call it a limp wall. In that case, and the mass is dominating as compared to the stiffness. That is not generally happening, but as per you know when you see something and a mass is more dominating than the stiffness, we just neglect the stiffness effect in the mathematical equation. So what we can define the mass law or limp law is that has only mass. In other words, the mass effect is dominant compared to the stiffness or internal damping. And we have some assumption as well when we deal with simple infinite wall. The first assumption is that the wall need to be harmonically oscillated. Acoustic pressure, density, and velocity are small enough to be linearized. The fluid particle on oscillate the mass particles that are in contact with, and the mass particle vibrate the fluid particles that they contact. We will understand after that. The fluid particles on the left and right side of the wall has to be same to such as velocity continuity. So let's understand that first, if I draw some particles against this wall on the left hand side, let's see that these are the fluid particles or air particles, you can say. They have against this wall left hand side, then right hand side we can draw some particles so that we can understand, right? So you can see this is the incident wave, which is strike to this wall with certain frequency. It's called omega, and we can define this incident pressure by this formula pi e j omega tx x minus c. This is the general formula for pressure wave. And when this pressure incident on this wall, these particles start vibrating with the same frequency of the incident wave, and the particle of the wall is also going to oscillate at the same frequency of this particle. And against this right hand side of the wall, the particle is also should be vibrating at the same speed or same frequency. And for why? Because we maintain the certified velocity continuity and the pressure continuity. So because here is the wall is is vibrating, or you can say the mass particles on the wall is vibrating, then we can define that the total pressure acting on the wall, pi plus pr minus pt, is minus omega square y. This is the ma. You can define it. M is mass per unit area, and this is the acceleration, omega square y minus I. Why this pi plus pr? Because pressure is a scalar quantity, so the total pressure is pi plus pr minus pt is total force acting on this plate, and this wall is also kind of vibrating. Then we can define as a ma, and when you solve this, you can get this formula. Then the velocity of the particle on the left hand side of the wall should correspond to the vibration velocity of the wall. That, so the velocity is defined because you know that the impedance is defined as a pressure divided by velocity. So velocity is p by z, pressure upon impedance. So the velocity, incident velocity, is this, and minus the reflection velocity pr by z0 is the velocity of the wall. And why this is minus? Because the velocity is the vector quantity. So we can say that pressure is incident in this direction, reflected in this direction. The total velocity is pi minus pr is equal to the velocity of this wall. And the same thing happening on the right hand side of the wall is pt by z0. This is the transmitted velocity, is also same as the wall velocity, or wall particle velocity, you can say. Then we can solve this two equation, this equation and this equation, because I also mentioned in the last video that we have three unknown and we have two equations, so we cannot solve this equation, so we always take the ratio. And in this case, we take a reflection coefficient is pr by pi, and you can solve this equation by this one and this one, and we get this equation. So we just you just try it by yourself, and you can definitely get this two equation, where r and t are the reflection and transmission coefficient of the respectively. The power transmission coefficient, which expresses how much power is transmitted related to the incident power, can be 1 by 2 pt vt. This is the power, and if you define with ut by this one, if I go back, is z equal to p by t, p, not p by t but p by u. So if you p is equal to p by z, so you can replace ut, u by p by z, and you can get pt by pi square. So the transmission loss is, we can calculate by this formula, t, it's a square bar z, you can calculate it definitely. Just try yourself. The transmission loss is known as 10 log 10 1 by tau square, and we can put it over here. And in this case, you can see here that transmission loss is totally depend upon the omega and m, and if both side is the medium is air, so z0 is also constant. And in this case, this omega and m0 is greater than, much greater than 1, so we can neglect this 1, and when you solve this problem, you can get RTL is equal to 20 log 10 omega by z0 d0. And when you take two scenario where transmission loss increase 6 dB, when you double the frequency, just take a two equation, keep it m is constant, z0 is constant, and when you double this frequency, the transmission loss increases by 6 dB. That is the case, you just keep in mind. to establish certain design guideline, because this is the wall, and this is a basic to design any wall for transmission loss or for noise control. Look at the frequency that make the transmission loss is zero. We refer as a block frequency. Block frequency means that at this frequency the transmission loss is zero. In this case, the all the frequency, all the noises at that particular frequency is blocked. Nothing is going to be transmitted through the wall. And when you can keep it like this one is one, then omega is equal to 2 pi by fb by m2z0. So then you can calculate with this formula fb. This is a block frequency, and z0 is 445 characteristic impedance at air. Then equation is become 132 by m. That is a very beautiful formula for calculating the block frequency. So these are the example, you can go through it. Like if you use a material whose mass per unit is 10 kg per meter square, that is very heavy, then block frequency is 30 meter per 30.2 hertz, and the mass law says that 6 dB for 1 vector, so you can increase this, and that estimated the 36 dB. So what is the conclusion of that is that if we want to suppress the lower frequency of the lower frequency of the noises, either you increase the mass of the wall, and that is not a practical requirement, because once you increase the weight, it's make heavier, it's very costly, and it's not realistic for suppressing the low frequency noises. So what we conclude over here is that theoretically and experimentally, it is observed that the traditional material can only provide good transmission loss at higher frequency, more than 1000 hertz. Traditional materials fail to perform at lower frequency. Means that our wall cannot be block the lower frequency noises or sound. There is another category, we call this for non-porous material, and this is a non-porous material. And for porous materials at low frequency, effective mass thickness with respect to the wavelength decreases, which reduces the transmission ratio. If you want a detailed video on this case, I will definitely, if you say something, if you want. Some resonators absorb are able to provide absorption low frequency, but the absorption is only limited to a few its resonant frequency, and the absorption magnitude is low. So what we can conclude here is that the final conclusion is that the traditional material cannot completely absorb or reflect sound, especially in the range of 100 and 1000 hertz, and that is the very critical for noise control engineer or scientist. In this case, this is a wall because this is a non-porous materials. In that case, the transmission loss and the absorption coefficient and absorption coefficient, you can say, is the same. And we definitely, as a noise control scientist, this is very difficult to control the noises under the frequency range of 100 to 1000 hertz with the help of conventional material. That's why the metamaterial technology comes into the picture. And so how we can define the acoustic metamaterial? So let's understand the first that acoustic material are engineered, that is artificial, you can say, engineered artificial structure with sub-wavelength microstructure. Sub-wavelength means less than the whatever the frequency you want to suppress. Provide unique property to control sound waves, such as achieving negative effective mass density and bulk modulus, which are not found in conventional material. These are the two governing factors for the metamaterial design. First one is effective negative mass density and negative bulk modulus. And in the conventional material, both are the positive, but in metamaterial, we can design in our structure in such a way that we can achieve this both, or either one negative or the positive and both the negative, something like that. The mechanism for controlling the sound in metamaterial is, I already discussed, effective bulk modulus and effective mass density through the periodic arrangement of this unit cell. And the bulk modulus, you can say that the resistance of the uniform compression, and negative bulk modulus implies that material expand when pressure is applied, which contradict to the everyday materials. We will understand in the next lecture that what is the negative bulk modulus and the mass density. And the let's define the mass density as well. The mass per unit volume is material. Mass per unit volume is of the material. And negative mass density means that when a force is applied, the materials move in the opposite direction of the force. Let's suppose if you have a mass and you apply the force, it's going, your object is moving in the direction of the force. But in the case of negative mass density, in that case, the mass is moving the opposite direction. That is also achieved, and we can understand with the help of some example in the next video. So acoustic metamaterial absorb performance depend only the geometric parameter. That is very important. Just remember that the absorption performance depend only the geometric parameter, not on the materials and not on the constitutive materials. It depends, because if your material is soft, maybe acoustic property little bit affect, but unless until it's hard, like if I take aluminum or something like that, or wood or 3D printer plastic, almost same. So mostly the acoustic metamaterials absorption performance depend upon the geometrical parameter, not on the constitutive material. Thank you.